Hi and welcome. My name is Harriet Wilson, and today I'm going to address the question, do extreme in-lake mixing events correspond to extreme atmospheric forcing? So to start with, I want to introduce this idea or concept that we have of a mixing event. So imagine this is a water column profile taken from a day in summer in a temperate lake. Because of the nature of density and temperature, you've got colder, denser water at the bottom and lighter, warmer water sitting on top. And in the middle, the steep density gradients of the thermocline act as a barrier between these two layers. In this idealized version of a stratified profile, the blue region at the surface, the epilymnium, is all the same density. This means that there's no resistance to mixing, and just a small amount of energy, typically from the atmosphere, can mix this layer. Important sources of mixing energy are mechanical energy injected into the water from wind, convective mixing, which occurs due to heat loss at the surface, and mixing due to the intrusion of an external water flow. Short-term mixing events may be characterized by subtle changes in the profile, and these often include cooling of the surface waters or a flattening out of the profile, which means a loss of stability, or a deepening of the epilymnium. Both theory and ad hoc empirical evidence have indicated that mixing events can be profoundly important in lakes. In this hypothetical mixing event shown, water from below the thermocline is entrained into the epilymnium, resulting in a replenishment of nutrients in the surface layer, a boost of oxygenated water into the bottom layer, and increased productivity. However, mixing events can produce many different biogeochemical effects, sometimes producing significant and long-lasting change for the biology of a lake. Another reason why mixing events are particularly topical is their influence on the exchange of gases with the atmosphere, including greenhouse gases and such as CO2 and methane. Therefore, mixing events may be particularly important in calculating the net emissions of lakes. So these are reasons why we're interested in them. The uptake of extreme event analysis in general in limnology has been particularly prevalent in recent years. In fact, a Scopus search shows that the terms lake and extreme events, including the terms lake and extreme events, showed a rapid growth in the number of studies in the last 20 years, shown by the plot at the top, which exceeds the rate of growth of limnology as a whole, shown at the bottom. The vast majority of these current extreme event studies, however, have primarily focused on climatic or atmospheric extreme events. And these studies typically identify extreme events as the tails of the cumulative frequency distribution for a single climatic variable, such as wind speed, precipitation, or air temperature. In contrast, only a small minority of studies focused on in-lake biological and physical extreme events. And these typically provided only an anecdotal definition of the event extremeness. This preoccupation with extremes occurring above the lake suggests a need for more analysis of in-lake extreme events. And in addition, the existing literature appears that there's this implicit assumption that there's a one-to-one relationship between the extreme atmospheric forcing, so that's the mixing energy going into the lake, and the in-lake response. And while this is a logical assumption, it has not actually been shown in the literature. And in fact, recent studies, as I've noted on the slide, are indicating the complexity of this. So in this study, we test the assumption that extreme in-lake events are the result of extreme atmospheric events. And to do this, we calculated extreme in-lake events using surface water temperature decline, epilymnium deepening, and profile stability loss. And we compared them to extreme atmospheric forcing events from 3 variables, which are commonly linked with driving in-lake mixing. And these are wind-driven mixing energy, surface total heat loss, and precipitation. So to summarize, the 2 research questions are, can we robustly define an extreme in-lake event? And secondly, do extreme in-lake mixing events correspond to extreme atmospheric forcing? We studied 2 European lakes, Loch Fyr, located on the west coast of Ireland, and Lake Erkin near the Baltic coast in Sweden. The lakes differed in many characteristics, including size, as you can see, depth, climate. Here we show the annual average water temperature at sensor depths for each lake. And you can see the difference in stratification dynamics here, with much larger annual water temperature range in Lake Erkin, while the stratification dynamics in Loch Fyr are comparatively weak. We used daily average data and had over 10 years of data for each lake. And meteorological data was also used, mostly collected on the lake. For the analysis, we defined extreme events as the most extreme 10% of days for that month over all years. Secondly, we assessed the level of agreement between the extreme in-lake variables. And then finally, we assessed the agreement between in-lake and atmospheric forcing variables. And agreement was calculated as the percentage of events occurring on the same day. We also validated our results using various alternative extreme event definitions and calculations. However, the key results remain the same, so we just present the core results here. This is a plot from Loch Fyr showing just one variable, and that's surface water temperature. The yellow region is the peak summer months of June, July, and August. April to May is referred to as the onset period, and September to October is the overturn period. The grey violins showed the distribution of the full data for each month using all years of data. And this indicates that the range in surface temperature daily change is an increase of 2 degrees to a decrease of 2 degrees. The most extreme 10% of declines in water surface temperature are the extreme events, and they're highlighted in orange, and the threshold for this is highlighted is the red line. Here we can see that the largest events occur in June, followed by July. If we look at all the in-lake variables, again for Loch Fyr, we can see that there's large variability in the seasonal pattern of extreme events between the different variables, indicating that they're finding events at different times. If we look firstly at epilimnium depth events, there's no clear pattern. However, there's noticeably larger day-to-day variability from April to June, and the largest events seem to occur at this time also. Schmidt stability has the strongest seasonal pattern, with the event magnitude substantially higher in the summer months. While these results show large differences between the in-lake variables, we also find little similarities with the atmospheric forcing variables shown in the figure on the right. And similarly, we find similar variability between all the variables in Lake Kirkham. So here we show the agreement between extreme events identified by each of the different variables. So these values here are the number of days identified as an extreme event by both variables, shown as a percentage of total possible matches. So for example, 57.7% of surface water extreme events were also Schmidt stability extreme events. So firstly, if we just look at the agreement between the in-lake variables shown in red, we find that for the majority of the time, different in-lake variables identified different extreme events. So if you use a different metric, you're going to find different extremes. And in fact, these are pretty low. And for epilimnium depth, we found that changes in the threshold value or the method also produced different extreme events. Now, if we just look at the agreement between the in-lake variables and the atmospheric forcing variables, we find even lower agreement, and overall total heat loss flux seemed to have the strongest agreement, while precipitation had the lowest number of matched events. We can also see the agreement between different atmospheric forcing variables, although this is not so relevant to our study objectives. So this result now calls for a closer look at these in-lake extremes. And here you can see a scatter plot where each grey dot is a day in our full time series. The y-axis is the total heat flux for that day, and the x-axis is the wind power. The grey ellipse represents the 95th confidence range for the whole data set. So if we superimpose the extreme in-lake events, we can see that the epilimnium depth events are in red, Schmidt stability events are in green, and water surface temperature events are in blue. What these graphs now show us is that firstly, some of these in-lake events may have multiple drivers, so they may be driven by heat flux and wind power, but neither of which are necessarily extreme. And this is quite an interesting sort of bottom-up approach to figuring out what is driving what compound effects or multivariate effects are driving these in-lake extremes. But secondly, a more noticeable portion of the data emphasized in red actually does not correspond to either heat loss or wind mixing events. And these include epilimnium deepening events, which we know can be problematic due to no objective definition, but also surface water temperature and stability loss events. Okay, so if we go back to the key findings now, our results show that in-lake events are not objective, and the identification and seasonal timing of extreme events is highly sensitive to the metric used. Therefore, by using a different metric or even just a different definition of the same metric, mixing events that you identify will be different. And so they're not obvious. In addition, by anecdotally referring to mixing events, as we commonly found in the literature, we're conjuring up this idea of that there's a classic mixing event, which is not necessarily supposed in the observed data. Secondly, we found that extreme in-lake mixing events rarely corresponded to extreme atmospheric forcing. This demonstrates that extreme events are much more complicated than a one-to-one relationship between mixing energy and in-lake response. And the reasons for this need to be further unpacked. These results are important because mixing events are part of the conceptual chain which shows how extreme weather events are influencing lake functioning. As we explained in the beginning, extreme mixing events have this reputation of driving ecological change in lakes and may be key to understanding the net emissions of lakes. However, as of yet, our understanding of mixing events is far less sophisticated than our understanding of extreme weather events. And we are not clear on the exact conditions, context, etc. that drive these mixing events, or how to measure them appropriately. Therefore, if we want to know the impacts of extreme weather events on lakes, we need a much more robust understanding of what is normal and extreme in-lake variability in different lakes. Thank you very much for listening.